Last time we were discussing the following. We had seen the character table, and we'll see it again, of S3. And there were 3 characters, which I think I called something like this. Here I have to write down the conjugacy classes. And the first 2 are linear characters, so are really characters of the group generated by 1, 2, and then I have this character here. And I was trying to see what's a representation affording this character, a representation such that its trace is this character. Recall that one of the seminars is about the problem, once you know a character, which is relatively easy to find, how to find the correspondent the representation in an algorithmic way, because here it's sort of a heuristic way, the one I'm using. So what we found, so if rho affords chi2, recall that this means that, what happens? Okay, that chi2 of G is the trace of rho of G. Okay, this means affording. It's the and then I probably need another parenthesis here. This is the character of this representation. Then what we have found that we can choose a basis, because recall that one of the many advantages that characters have is that there can be many representations which are isomorphic, different representations which are isomorphic, whereas two character, all the isomorphic representations give the same character. Okay, so equality of character is equivalent to isomorphism of representations. So we have found that with respect to a suitable basis, which we try to have as simple as possible, say rho of 1, 2, 3, let's write it correctly, or 1, 2, 3, can be taken of this form, okay? Where I'm not writing the 0 of the diagonal, which means, recall the argument, I wrote down the argument last time, so I'll just recall it briefly. Rho of 1, 2, 3 must be a diagonalizable matrix which eigenvalues which are third roots of unity. You know that the sum of the two eigenvalues, the trace, is -1. And then you see that the only possibility is that the two eigenvalues are omega and omega square. So you take as basis the two eigenvectors, okay? And recall, of course, that we still have a choice, because I mean, if we take, for instance, a multiple of one of the a non-zero multiple of one of the eigenvectors, is still an eigenvector. And then by considering the fact that that if you conjugate 1, 2, 3 with 1, 2, you find 1, 3, 2. Yes, okay, you find this. Well, you find 2, 1, 3, which is then 1, 3, 2, and this is the inverse, okay? And this can be written as 1, 2, 1, 2, 3 equals 1, 2, 3 inverse 1, 2, okay? Then we found that with respect to the same basis, we have found that 1, 2, yeah, you apply rho, so you have rho 1, 2, rho 1, 2, 3 equals. We have found that with respect to the same basis, rho of 1, 2 is of the form lambda mu. Let's write the zeros here. So essentially what this relation tells you is that is that the eigenvector of an eigenvector with respect to the eigenvalue omega is sent by this to an eigenvector with respect to the eigenvalue omega squared, and conversely, okay? With respect to the same basis. So far, we have just chosen the basis like this. But then note, this is an element of order 2. So rho of 1, 2 square is the identity matrix. And this is, of course, lambda mu, okay? I'm not writing the 0 because 0 lambda times 0 mu gives you lambda mu, and the same here. You want this to be an identity, okay? So this means that mu is lambda inverse or vice versa, okay? Note that this has trace 0 as it should be, okay? The trace is 0 here. Good. So we have found that rho 1, 2 is this. But we can be even more precise because let uv be the basis we are working with. So this means that u is an eigenvector for rho 1, 2, 3. Let's write it here. And v is an eigenvector for rho 1, 2, 3 with respect to the eigenvalue omega square. I didn't finish the first sentence, but this is what we have here. And here what we have, so I write the vector on the left and the operator on the right. And here what we have that u rho 1, 2 is lambda v, and the v rho 1, 2 is lambda inverse u, okay? Exchange. But now define another basis, change the basis. Let u v prime be another basis where u is the same and v prime is lambda v, okay? Of course, lambda v is still an eigenvector for rho 1, 2, 3 with respect to omega squared, because if you multiply by lambda on each side, you get this, okay? So u is the same u, but you have changed v. So what happens here? U rho 1, 2 is v prime, okay? But we define like this. What is v prime rho 1, 2? Okay? So is lambda v rho 1, 2. This is a linear map, so this is lambda, and what's this? This is lambda inverse u. So this is u, okay? What we have found with respect to the basis, I haven't organized the space very well, with respect to the basis, u v prime, we have the rho 1, 2 is simply, you see, rho 1, 2 sends u to v prime, so 0, 1, and v prime to u. And so we have found a very simple thing. I mean, you don't need to have lambda and lambda inverse, you just need two ones. And we have changed basis once, seeing that we have different representations which give the same character. Because I mean, if you write like this with every possible lambda, the trace is always 0 because you have 2 zeros here. And this is the same here. But the character is the same. The representation with respect to uv or uv prime are isomorphic because it's just a change of basis. The character is the same. This is one of the advantages of character. So in the end, what we get is rho 1, 2, 3 is omega squared, and rho 1, 2 is 0. Okay, I'm writing the zeros as well. And then the other elements you can calculate because these are just product of 1, 2 by a power of 1, 2, 3, or, okay? So we have found the representation, and here the trace is -1, and here the trace is 0. Good. And we'll see more examples in a second. But before we we consider more examples, we want to see a technique which allows us to find certain irreducible representation, in particular permutation groups, quite quickly. This is also a nice application of what we know about so far about characters. So remember that we have used the term permutation representations in two ways, in a sense. Well, let's put it like this. Suppose let G be a finite group. Okay, well, this is sort of a blanket assumption that holds throughout the course, and which acts on a set omega. Okay, so it's the typical action which we denote with the usual symbol alpha to the G, where alpha is in omega and G is in G. Then we obtain from this a linear representation, which we obtain in the following way. Let V be a vector space with basis omega, the elements of omega, okay? Then G, then the permutation representation of G on V induced by determined by the action, is simply given by alpha rho G equal alpha to the G. So remember, this is a vector space with basis omega. More about this in a second. So this alpha in omega is a basis element. And of course, we know that to declare a linear map on a vector space is enough to declare the action on a basis and then extend by linearity. And we declared that the action of rho G, very much like in the case of the regular representation, is exactly the action. I mean, you have an action, what G does this in the action, okay? If you want a vector space with basis omega, V can be taken as the space of functions from omega to the complex numbers. This is very much the same as the group algebra, okay? Because the group algebra was defined as the set of functions from G to the complex numbers. And then we found that the delta function, the Dirac function, the Dirac delta functions behaved like the elements of G. And in this case, it's just a vector space. And it's the same. I mean, the base is not given exactly by the elements of omega, but rather by the deltas, okay? So delta of alpha being the function that is 1 on alpha and 0 on all the other elements of omega. But so this space of function as a basis which is in one-to-one correspondence with the element of omega. It should be rather clear. Let me write up here. Okay, so delta of alpha on, say, beta equal 1 if beta equals alpha, or 0 if beta is different from alpha. And these are a basis of this space, and they behave. So when I say a vector space with basis omega, really this space as a basis, the delta alpha for alpha in omega. Okay, so it's in a one-to-one correspondence. Okay, so this is what you do. You have a G acting on a set omega, and you consider a permutation representation determined or associated to the action, which does this on this basis. Okay, and of course, so let's for instance, well, okay. So the problem, of course, is what's the character of of such a rho G, of such a rho. Okay. Well, so the idea is that you have a matrix. Our vector space has as a basis the element of omega. So let's, this rho corresponds to alpha in omega. And alpha is sent to another element. Which one? So this is rho G, okay? Is sent to what? Is sent to alpha to the G, to the unique element, which is again an element in omega, in the basis, on which G sends alpha in the action we have in the beginning. So this means that we have all zeros, and we have one here in the column alpha to the G, and all the rest are zero, okay? Because this is a very particular, permutation representation means it's the simplest possible linear map in a sense, because you send the basis element to a basis element, not to a linear combination of the basis elements, okay? So there are all zeros and then a one, because alpha is sent to alpha to the G. Now, what is the trace of rho G? Well, the trace is the sum of the elements on the diagonal, is the number of elements on the diagonal, number of ones on the diagonal. Okay? But when is it the case that we have a one on the diagonal? We have a one in the diagonal when this one in the row labeled by alpha is exactly in the column alpha. Okay? So equal to Fg, which is the number of fixed points of G. So Fg is the number of alpha in omega such that alpha G equal alpha, okay? Because you have one on the diagonal, on the main diagonal, when in the row alpha, the one is also in the column alpha. So alpha alpha, main diagonal, okay? So this is the character. We will call it chi G, but it's Fg. So the character of a permutation character is the number of fixed points, okay, of the element in the action. Very simple, okay? Just to take a particular example, which we will use to compute the character. For instance, if G is S3, acting naturally on 1, 2, 3, on omega equal 1, 2, 3. Okay, so we ask ourselves how many elements are fixed by 1. So this is the number of elements of omega fixed by 1. Well, of course, this is 3, because the identity fixes everything. What's the number of elements fixed by 1, 2, 3? We only need to check an element per conjugacy class. Of course, 0. Okay? Because 1, 2, 3 doesn't fix anything. What's the number of elements fixed by 1, 2? Well, 1, because this element moves 1 and 2 and only fixes 3. And we'll see that, so these are the value of a certain character, which is not irreducible, because we had seen that S3 has only irreducible characters of degree 1 and 2. But we'll see how we will able, from this character, to obtain the other character 2 minus 1, 0. Okay. Now we want to do the following. We want to find a formula for the number of orbits of G on omega. And the formula, this is called Cauchy-Frobenius, if I remember correctly. Frobenius, yeah. And it's a curious formula. I'll first prove it. Perhaps you'll find it already in other courses, but it's a curious formula for certain reasons. Let's see what this formula tells you. Let's say we'll prove the formula and then see what it says. Okay, so we consider omega times G. Okay, so all pairs where the first item is in omega and the second in G. And in it, we consider the subset of pairs alpha G such that alpha is fixed by G. Okay? So we consider the pairs, not all pairs, but the pairs when the element G fixes alpha. We now employ a very standard but quite nice argument in combinatorics, which is the double counting argument. That is, we have this square, omega times G, okay? And we have these elements alpha G. We count first by row and then by columns. We count once by row and once by column. Okay? So we first count by row. So how many elements of this set, let's call delta this set, okay? Consider the row alpha, labeled by alpha, okay? So you fix alpha, and we ask how many elements of delta? Are in row, in this row. So we fixed alpha. So alpha G, for alpha fixed, is in delta if and only if alpha to the G equal alpha, which means if and only if G is in the stabilizer of alpha, okay? So what we found that the number of elements in this row are G alpha elements of delta. Okay? We are counting by row. So in the alpha row, there are exactly as many elements as the elements of G which fix alpha. Because I mean, once you fixed a row, the elements of this row are labeled by the element in G, and such an element, alpha is fixed, is in delta if and only if G is in G alpha. So this means that one way of counting delta, if we count by row, okay, is the sum over all rows, okay, of G alpha, okay, sum over all rows, because the rows are indexed by the element of omega. However, so what's this number? Well, suppose that that the orbits, well, I have to write it here, and then I will continue here. Suppose that the orbits of G on omega are given by our beta 1 to the G, and so on until beta, let's say k to the G. Okay, so there are k orbits. This is an orbit, the orbit of beta 1 and the orbits of beta k and so on. So this can be written as sum for I that goes from 1 to k, okay? And then sum of G alpha for alpha in beta e to the G, okay? So you know that the orbits are a partition, okay? Form a partition of omega. And so I'm using this fact. I'm summing, I'm partitioning the alphas in the various orbits, okay? And I sum over the number of orbits, okay? So I've found this fact here. Now it's better for me to copy to the next, okay. So this, I'll have to copy add to next page. Okay. Oh, I've lost something, but let me write it. So this is alpha in omega, I from 1 to k, and here alpha in beta I of g. Okay? But recall that so if alpha is in the orbits, then alpha equal to beta I to the g for some g. And then we know from group theory that g alpha then is g beta I to the g is nothing else that beta I to the g, the conjugate. Okay, this is conjugate. And of course, this means that since this is a conjugate, the order of the conjugate is nothing else than the order of g beta I, okay? Because there are a conjugation is a bijection. So what we are finding that this sum here is the sum for alpha and beta I to the g. All these g alpha have the same order, which is the order of beta I, a fixed element in the orbit. But now look, we now have, consider the inner sum between parentheses, is the sum over alpha of these things. But these things do not depend on alpha anymore. These are constant because we are in the orbit of beta I, so this is a constant. And how many summands you have here, the number of elements in the orbit, okay? You have as many summands which are equal to the order of g beta I, of the stabilizer of beta I, as there are elements in the orbit. So beta I to the g. But now look, what we have here, we have orbit stabilizer. And the orbit stabilizer theorem tells you that the product of the size of an orbit times the size of stabilizer is the order of g. Okay, orbit stabilizer, okay, orbit stabilizer. But once again, we have the sum from 1 to k of a constant which does not depend on I. So this is simply k order of g, okay? So we have counted delta by rho and found that the number of elements in delta is k times g, the order of g, where k is nothing else than the number of orbits of g on omega. And now we count by column. So this time we fix a g here and we consider all the alpha g which are in delta, okay? Fix g, okay? Alpha g is in the column, it is in delta, if and only if alpha to the g equals alpha. But this time g is fixed, so if and only if alpha is fixed by g in the action. And we had a name, well, not for this set, but for the number of elements. And so in the column labeled by g, there are f of g elements of delta. Because in the column indexed by g, labeled or indexed by g, there are as many elements in delta, as elements alpha which are fixed by g. And we had written f of g for the number of elements of omega fixed by g. And so counted by columns, we get the order of delta is the sum for g in g, because we are running over the columns f of g. And we had found in the previous calculation calculated by Rho that d equals k times g, and so Cauchy-Frobenius it's sometimes referred to as a result of Burnside, but it's really Cauchy-Frobenius tells you that k number of orbits of g on omega is, as you see, an average of the number of fixed points. So it's funny because, I mean, this is the number of orbits. So, I mean, number of, say, an orbit is something that is moved around by g, and here you're counting the fixed elements. Sometimes, I mean, it's, you're not supposed to laugh at this joke, but this is referred to as counting the number of cows in a field by counting all the legs and dividing by 4. The average here, because you're counting a big number and then divided by the order of g. But as you see, this will be extremely important fact. Why is it so? Because now I rewrite this as 1 over g, sum g in g, 1 times f of g. Well, this looks harmless, but these are the values of the trivial character. Remember, the trivial character is the character of degree 1 associated to representation of dimension 1, in which you send every element of G to the identity 1 times 1 matrix, which has, of course, trace 1. So you see, of course, I can put a conjugate here because the conjugate of a real number is itself, and this is the character of the permutation representation associated to the action. Okay, so k of g equal fg is the character, is the permutation character. So a character associated to the action. There's an action. So what's this? This is nothing else by the inner product of 1 with kg. Chi. I mean, I'm summing over chi. Okay, so this is the number of orbits. This is this important formula. So you see, you have a group acting on a set. You wonder how many orbits you have. And what we found that this is the inner product of the permutation character with the trivial character. I mean, there was no reason whatsoever to consider character representations, but they enter in this. And how do we formulate this? Well, you see, let me repeat this point because it's very important. I mean, at the risk of being boring, if rho, no, let's boring, but in black. If rho is a representation, and we write it as the sum of irreducible representation of a direct sum representation, and rho is equal to rho 1, 1 plus rho 1, 2 plus rho 1 and 1, say, plus rho 2, 1 plus, and so on, plus rho 2 and 2, and so on. Okay, this is clear what we are doing, where all Rij are irreducible. Okay, and we have that rho I, say, rho I S is isomorphic to rho I T for ST, for any ST, but rho IS is not isomorphic to rho JT for I different from J. So I have written rho as a direct sum of irreducible representations in which all these are isomorphic, okay? All these are isomorphic and so on, but none of this is isomorphic to any of this, okay? So I have grouped together all the isomorphic representation here. But then if we consider the characters, if chi is the trace of rho ij, and note that the character, remember, this is an important fact, only depends on the isomorphism type of the representation, because all these are isomorphic, so the characters are the same. Then we write this as rho equal n1 chi1 plus n2 chi2 plus so on, okay? Where the chi are distinct, okay? Chi distinct from chi j, for I different from j. So the fact that the representations are not isomorphic means that the characters are distinct. Isomorphism representations or irreducible representations corresponds to equality of characters, okay? And then the point is that when you consider the scalar product, the inner product of chi with rho, okay, this will be by the orthogonality relation exactly ni, okay, by the orthogonality relation. Why? Well, because what we have here is chi n1 chi. Okay, let's. Okay, so these numbers are integers. So we get n1 chi chi1 plus n2 chi2 and so on. And the point is, the orthogonality relation tells you that all these inner products are zero except chi, okay? And this will get you ni, okay? This, I hope this is clear because it's very important, okay? So the only non-zero, this will all be zero, except that somewhere you'll have ni, chi, and this is one, and so you get exactly ni. So you want to know how many times an irreducible representation appears in a direct sum representation of a certain representation. You take the character, okay? And of course, sorry, okay, since this is important, so chi, let chi be the trace of rho, okay? The character associated to rho, okay? And so this is the chi, okay? So if you take this is not rho, it's chi, okay? So it's the character associated to the representation. So if you take the inner product of chi with this character, you get exactly the number of times the representation appears in rho, and the number of times the character appears in here. Okay, so this is a very important point. Sorry for the confusion here. I had forgotten to take the trace here. So chi of g equals trace of rho of g. Okay, so let's say it again. If you take a character and take the inner product with an irreducible character, you'll find the number of times this character appears in the character, the number of times this representation appears in rho. But remember what we have just found. We have found that this scalar product is k. So this means that the number of orbits, thus, next, thus 1 chi, where chi is the permutation character associated to a certain action, the action we are speaking, equals to the number of orbits of the action. Okay, but this tells us that, say k, this tells us that in k, when you write k as a sum of irreducible characters, okay, meaning that chi will be k times 1, okay, this is the trivial character. This is also the trivial character. The character which takes value 1 on every element, plus other irreducible characters distinct from 1. Because this inner product tells you how many times 1 appears when you write chi as sum of irreducible characters, okay? This tells you how many times the trivial representation appears when you write the representation as direct sum of irreducible representations, okay? There's an important particular case. So G is transitive on omega. That is, G has 1 orbit. If and only if k is equal 1, so 1 equals 1 chi, okay? Which means that chi equals 1 plus another character, the sum of the missing character, where 1 does not appear in psi. So the trivial character appears only once when you write chi as a sum of irreducible characters. There's a term that I have forgotten to use, the chi, okay, fine, okay. So, okay, let's put it like this. If chi is a character, if chi is a character, an irreducible character is said to be, an irreducible character psi is said to be a constituent of chi if the inner product is different from 0. That is, if psi appears in the composition. Well, no, let's use phi because otherwise it clashes with this. An irreducible character phi is said to be a constituent of chi if the inner product is different from 0, which means that phi appears in the decomposition of chi as a sum of irreducible character. So here we have that 1 is not a constituent, of psi, okay? So this is important. G is transitive if and only if chi can be written as 1 plus some of other irreducible characters, but what's important in this, I mean, the sum that's here, 1 is not a constituent here. It does not appear here, okay? I mean, you can see it because, I mean, when you take the inner product, chi with 1 gives 1, and then 1 with psi has to be 0, okay? So let's write this on the next page. So if chi is a permutation character, is the character of a transitive action, 1 orbit, then 1 chi, okay, then this character is equal to 1 plus psi, where, and let's put it like this, 1 psi equals 0. There is 1, the trivial character, 1 is not a constituent of chi, of psi. And then let me just announce the result that I will be proving tomorrow. We will prove that, to be shown tomorrow, psi is irreducible if and only if the action of G on omega is too transitive. So transitive means one orbit, okay? Two transitive means, let me recall, that is, let's put it like this, given alpha, beta, gamma, delta in omega, with alpha distinct from beta and gamma distinct from delta, then there is G in G, such that alpha to the G equals gamma and beta to the G equals delta. That is, say, is more than transitivity, because not only you can bring any alpha to any gamma, but if you take a pair of elements which has to be distinct, you can take this to any pair of distinct elements. Of course, you have to take distinct elements, because if you take alpha equal beta, you cannot take alpha to gamma and beta to delta if these two are distinct. So you start with two distinct elements and you end up with two distinct elements. And the important point that we will recall tomorrow is that as n is too transitive for n greater than or equal than 2, okay, let me think, yes. And yes, well, okay, and an is too transitive for n greater than or equal to 4, okay? So Sn and an, so the symmetric and alternating group are too transitive, and we'll see that, that this allows us to find irreducible character in this form. And in particular for S3, we will find that the character 2 minus 1, 0, we have already found with the orthogonality relations, also comes from this recipe. But more about this tomorrow. That's all for today, and thanks, and see you tomorrow.